like to thank the organizer for giving me this opportunity to give this talk. So I will more or less focused on the physics that is behind to solving this so-called RAA versus V2 puzzle for a long time. Even though the focus of my talk here is mainly on just light hadrons, charged hadrons, but I think similar physics also will occur in heavy flavor. And my collaborator, I think, is Xin-Nian will focus on the heavy flavor part of this. And in this talk, I will mainly just look at, as the title said, from jet quenching to recombination and the hydrodynamics. So we all know that we have a couple of props of the PGB property in heavy ion collisions, and one kind is what we call soft props that rely on the consequences of collective flow to probe the properties of bulk matter, like for example transport coefficients, equation of state. In the meantime, we also have the other set of tools that is involving hard props, in particular how the fast quark is traverse the dense medium, how they interact with the medium. That will give another complementary point of view of the properties of quark and plasma. And on the collective part, so far the consensus is that hydrodynamics can provide a very decent and sometimes very successful description of the collective phenomena that we see in experiments. And you can view this hydrodynamics essentially is a effective theory that is only valid for most of the integrated over the low momentum part of the spectrum. And it is just set of closed a set of equation differential equations closed with the equation of state that we can normally use the parameterization of QCD, lattice QCD calculation, for example. On the other hand, you also have to provide information about transport coefficients, for example, the bulk and the bulk viscosity and shear viscosity. And in addition, you also have to provide the initial condition, for example, what is the initial energy density and the flow velocity field that you produce. So, but suppose you give this initial condition from Potter model, and then you can compare to the experiments, and that's how you can extract the transport properties, coefficients, for example. And this approach has been so far very successful. And here we show a comparison of the anisotropic flow, and not only V2 but V3, V4 as compared to data, and where you roughly can extract, for example, here the shear viscosity over entropy density ratio. And this is the latest, I think, the state of art comparison or extraction of the transport coefficients from the experiment data by the Jetscape collaboration, and this is with the Bayesian inference, with very, very careful inclusion of data errors and the model and in particular model errors here. And on the left side is the bulk viscosity, on the right side is shear viscosity. And within an error bar, you cannot really say there is a temperature dependence, but clearly somehow if you look at the shear viscosity around the phase transition region, there is the error bar is smaller, and which is a little bit different. You can expect could be different from the low temperature and also from high temperature. And on the other hand, you also have jet quenching, and jet quenching essentially describe is the phenomena behind the suppression of high transverse momentum parton and also suppression of jet. And it is caused by essentially a parton propagating through the medium with multiple scattering and transverse momentum broadening. And if you look at what is the theory behind this, and essentially there is basically like energy loss, both radiative energy loss and elastic energy loss. And they are all related to a quantity what we call the jet transport coefficient. It's a Q hat. And Q hat phenomenologically is related to the transverse momentum broadening square of a fast parton per unit length. And theoretically, you can relate this to essentially the glue density distribution inside your media. So this is somewhat kind of fundamental quantity that you want to describe the Quark-Gluon plasmid. So in this case, by looking at the data comparison, you can also extract this Q hat. And in the past, I think JetScape collaboration and formally Jet collaboration has done this, and we look at essentially mainly through the suppression of single inclusive hadrons here. And here is the summary of that study, and you find that to a certain extent, with different, even include different model uncertainties, you find out that the Q hat is about 1 or 2 GeV square per Fermi, around above the phase transition temperature. And also we know that from DIS, deep inlet scattering, this quantity is much smaller. It's in fact 2 orders magnitude smaller in the cold nuclear media. And this clearly tells you that there is really some kind of phase transition that changes the number of degrees of freedom when you go through from the cool nuclear matter to high temperature matter that you create in heavy ion interactions. But there is really uncertainty here around the phase transition temperature, and there are many models, for example, propose that there could be very sharp, a peak in order to describe the V2 of jet and the RAA of the suppression, in particular in intermediate region of PT. So this is the focus that my talk is, and from here you can see that you can divide essentially the hadron spectrum into soft part, which can be described by hydrodynamics, and there is high PD part that more or less can be described by the energy loss mechanism, and from there you can extract Q hat. But between this, in the intermediate region, and this is what I call the no man's land, and essentially it's very difficult to have a theory frame that can consistently describe both the soft and hard and the transition between this. And so here is what we're trying to do. And there are 2 phenomena you have to really take into account. One is that in this intermediate region, you also have to consider probably the interaction between jet and the medium. And this is essentially first proposed by a couple of people in the early 2000s, and that you can imagine that one jet is propagating through medium and deposit energy into the medium, and that energy will essentially propagate, and that will create what we call so-called Mach cone in the medium. Because the velocity of the light quark is much faster than the velocity of sound in the Quark-Gluon plasma. On the other hand, you also have to, there is another phenomenon you have to take into account, is essentially in this intermediate region is the parton recombination. And also around that time that people find that in order to describe the particle ratio, for example, baryon versus meson, and then you really have to take this kind of pattern recombination into account. That is, many people believe, is responsible for the observed the constituent quark number scaling of the V2, for example. So, so the model we use is the building block we use is the linear, what we call LBT model. It's a linear Boltzmann transport model to describe the propagation of parton, jet partons, and that has include both elastic scattering and also induced radiation here, and then in this model, we actually we trying to focus that we trying to describe the propagation and the interaction of the parton for jet shower, and also the recoil parton, the parton that is excited by the jet interaction, that they will also propagate through the medium. So both of the interaction between shower parton and the medium of the recoil parton are described in the same framework. And then on top of that, we decided to also have this coupled LBT model. So in this case, we want to describe the loop momentum, essentially, of the parton, including the soft partons coming from jet, because their energy so low, they might be thermalized in the medium, and then they become part of the bulk medium. So this we want to describe by hydrodynamics. So in this case, this hydrodynamics has a source term. The source term essentially is fed into by this Boltzmann transport for the parton, which is in the rest frame is below certain cutoff here. And then we just evolve this two equation, at the same time, they are sort of like synchronized in terms of propagation time. And the hydrodynamics, we used the in-house developed CL whisk hydro, and that can be put on the GPU supercomputer. That's only possible. That makes this kind of coupled equation approach possible, because otherwise it's really computing intensive here. And the last one, we have included parton recombination essentially at the freeze-out surface, plus jet fermentation for the very fast partons. And finally, for the formed hadrons, we also fit them into URKMD model to carry out the final hadron cascade in the medium. So here is an example. This is the ideal case when you have a quark, for example, propagating through a static uniform medium, and you can clearly see this is the energy density of the recoil partons carried by recoil partons. You can clearly see there is this even within the transport mode. You can see the propagation of this Mach cone, of this Mach cone, in fact, and you can imagine that this part of the medium excitation, especially when you look at the jet suppression, some of the medium excitation will be within your jet cone, and then when you do jet reconstruction, your detector does not really discriminate whether this pattern is coming from the jet or is coming from the medium excitation. So you really have to take that into account. And this in this particular study, we demonstrate that in order to describe the observed jet suppression at reality from 100 GeV to almost 1 TeV, you really have to take into account this medium response. And without the medium response, you find out that the effective jet energy loss is much bigger, because the leading particle loss energy is getting into the medium, and some of them is somehow coming within the jet cone. And when you do jet reconstruction, you recover that energy again. So the effective jet energy loss is become a little bit smaller as comparing to without medium response. And this is very important to take into account. And then when you do this, you can say that you can not only describe the RAA, but you can also describe the jet vector. So this here is, I want to emphasize that when you do the jet physics, you only look at the jet energy within the jet cone. So in this case, this kind of observables does not really care whether you have recombination or not. So it's not sensitive to the physics. What I'm going to talk about this parton coalescence. So next one we want to look at is to look at the correlation between the triggered event, for example, the Z boson and gamma jet, for example. And here, when you look at the jet construction, reconstruct jet, so this model, of course, can describe the energy loss. So this here is the asymmetry distribution of the gamma or Z jet, and for fixed momentum of the trigger. And in particular, if you look at on the right side, there's really indeed a shift in the transverse momentum of the jet. And roughly speaking, this essentially, the shift of the peak essentially gives you an estimate of the net momentum and the energy loss of the jet. And then if you look at inside detail, if you look at inside the jet, and you find out that most of this, the loss, most of this modification of the medium, the suppression of the leading hadron, for example, is described by on the right side is the fermentation function. You can clearly see there's a suppression at a very large PT, the large momentum fraction, and then there's enhancement at low energy transverse momentum. So this is where the energy momentum comes in. You lose particle, the leading parton lose energy, and their energy essentially more or less is recovered in the low momentum enhancement. And this enhancement also comes in towards in the large angle, not in the direction of the leading parton, but at some angle away from the leading parton, close to the edge of the parton, and also definitely they will also go outside the jet cone here. Similarly, here you can see this Z hadron correlation. But the thing is that to separate the medium response from the induced soft Gluon radiation is very difficult. If you look at inside the jet cone, both of them will contribute. Okay, and the medium response, of course, the energy is more or less on the order of the medium temperature modulo the flow velocity. And then if you look at the average energy of the medium induced Gluon, their energy, if you take into account the formation time, for example, this formation time has to be, constrained, this 2 omega over K squared. And if you require this formation time has to be on the order of like the mean free path in order for this radiation to happen. And that gives you some kind of constraint of the average energy of the parton given the Q hat here. And this, if you do some kind of estimate, this also on the order roughly on the order of temperature. So the energy of the soft radiation and the medium response is roughly the same. So it's very difficult. It's impossible to separate them within the jet cone. So one really probably have to look at outside jet cone here. So here is what we proposed. So for this Z hadron correlation, for example, instead of looking at within the jet cone, which is when you look at Z hadron correlation, instead of looking at the peak here, one should look away from this. And this data is the latest analysis from CMS. And somehow, in the beginning we were puzzled because we expect there is some kind of depletion because of the diffusion wake of the jet cone. But here, instead, you see enhancement. So we were puzzled a little bit. But after we look at our simulation, we see the similar thing here. There's also enhancement even away from the jet cone here. it turns out by looking at detailed analysis, it turns out, okay, this enhancement also happens in PP case. Okay, so well, it's not enhancement. And so in this part, in PP case, there is also some kind of non-vanishing correlation away from the jet, but this correlation is enhanced in A interaction. So it turns out this is due to the what we call MPI, the multiple parton interaction problem. So in PP case, this contribution essentially comes from MPI. MPI is essentially nothing but just the miniatures. They are independent miniatures. They are independent of miniatures with no correlation in angle with the trigger, but they are there. Okay, and those jets also have to suffer, jet interaction. And if you only look at the soft part, the soft momentum part, they are enhanced. So this is the enhancement, where the enhancement comes from. But if you find a way to subtract this and indeed find out that indeed should be some kind of depletion because of the diffusion wave. And then we went on further on, we trying to trigger some events. For example, that will have this diffusion wave enhanced, because normally if you only look at normal events, they are completely overwhelmed by the background, in particular by the MPI interaction. So in this calculation, we restrict the jet gamma jet asymmetry to be smaller than certain value. So in this trigger, you really require there is a minimum amount of energy loss of the jet, which means that the jet has to go through certain lengths of the medium. And in addition, we also have what we call, I don't have time to talk about this, we also have this transverse momentum asymmetry, which we developed, we call the transverse tomography. And this essentially require there's energy loss, the transverse browning, because there's a medium multiple interaction, there is like a diffused, what is it called, asymmetric diffusion, because the gradients, the transverse gradients of the density. So when you look at this, then when you take both of this, and indeed you can see, first of all, there is some kind of, when you trigger this, because the increased length, you have enhancement, of course, in the jet direction. But this one contains both the medium response and also induced radiation. But if you look away from the jet, there is a really depletion. The depletion essentially is coming from diffusion. On the right side, you can see there's a illustration here. This by the blue color of energy density. That essentially is due to the diffusion wave. Okay, and so with this kind of triggering, what we call two-dimensional tomography, by selecting those events, you enhance this kind of signal. If you can measure this, that will be unambiguously the effect of the medium response. So now we come to the single inclusive hadron spectrum. And in particular, you fix on, if you look at the intermediate PD region, so as I said already, you really have to take into account coalescence. And to some extent, the final hadron cascading will have effect. So within the latest model, we took this kind of hybrid approach. For example, we described we considered if the PD for PD smaller than certain cutoff, and those kind of hadrons essentially we describe by the CL-VISC 3D hadrodynamics with the medium response included. And then on the top of that, we include a coalescence model that includes both thermal correlation recombination and thermal hard, thermal and hard parton and hard parton correlation here. At very high PD, of course, the system, the physics is completely dominated by the jet fragmentation, and this is carried out by using the lone fragmentation within PTF. And then after all the hadronization, all the hadrons are fit into the UCAR-MND for the final hadronic evolution and also decay. So here is the hadron spectrum, for example, in lead-lead interaction at 5 TeV here, and this model describes the hadron spectrum quite well, but you can see the different component of the contribution. For example, at low PT with the dashed line, this essentially is a hadron contribution here. And then there is a coalescence that, let me see, the dashed line, the dotted line, essentially, the dotted line here is a fermentation. They are essentially dominate the high PT part. And then in the intermediate region here, the coalescence, the dotted dashed line, will it become really significant here. And then, long behold, if you look at the RA, we plot RA now on the top curve here. So since the low PT is given by hydro, of course, and hydro is known to describe the spectrum quite well. And then at a very high PT, we can describe the suppression of leading hadron also quite well. And then it's just in the intermediate region. So this kind of approach, hybrid approach, can describe the transition between hydro and high PT jet separation quite well. Not only the RA, but finally we find that you can also describe V2. Okay. So then we can look at the detail of this, and by looking at the flavor dependence, for example, of the hadron spectrum. And as we know before, this is in the early 2000s, people already know that this recombination can modify and will modify the flavor decomposition. And similarly, this in our case is not surprising. We can describe, for example, the enhancement of proton to pi ratio here as compared to PP case. And there is also a little bit enhancement of cation to pi ratio. And then what is interesting is that if you look at the V2, the flavor dependence of V2 here, and this can also describe the flavor dependence of the V2. And you find out that the coalescence model really enhance the V2 of the baryon here. And in particular at intermediate region and PT region here, and at both centralities, and even in further peripheral interaction here. And then without, if you go without the coalescence model, essentially you cannot describe in this at high PT, one can more or less can manage to describe, but in the medium PT region, you really miss the experimental data here. So this is really an illustration of the importance of different physics component when you want to describe the hadron spectrum, the RA, and also V2. And here we demonstrate there is really no need, and this kind of our model can describe this this data quite well. There is no need to introduce some kind of crazy temperature dependence of the transverse, of the Q hat, the jet transport coefficient here. Okay, so here is my summary. So within the coupled, LBT model, we can describe the hadron spectrum from low PT, from not low PT, from low PT to high PT quite well. And we demonstrate that the coalescence, the pattern coalescence is very, very important to describe this data, in particular to solve the RA and the V2 puzzle at intermediate PT. And such a coalescence is also important to describe the flavor dependence of the spectrum and also V2. And then we also demonstrate that the medium response, the jet response to the to the jet interaction is also leads to the enhancement of salt hadron inside the jet. And in particular, the ambiguous signature of this medium response is the depletion of soft hadrons away from the jet. And we have developed what we call the two-dimensional jet tomography to so that we can focus on the event that has enhanced length of propagation, so that the angular structure of Markov become really visible. So we are very excited to look forward to our experimental colleagues, so that they can actually find a way to apply this kind of two-dimensional jet mockery to their data analysis. Thank you very much for your attention.
Thank you. Thanks. We have some time for questions. So you decide, either Jörg or Elena. Yes, and then ENG from outside. Let's start in the room.
Hello, Xin-Nian. So very nice review. I have a question to theoretical part of your talk.
Yes.
Can you separate the contribution from radiative and elastic scattering, for example, when you discuss in Q-hat or when you calculate array? That would be interesting to see the importance of different mechanisms.
Yeah, well, from all aspects of the consequences, there is really not a difference here. Within, at least within the jet cone, I mean, there could be different angular distribution within the jet, but they are really mixed together. And as as I'm trying to demonstrate here, the energy spectrum is also very similar. So and then you can look at the length dependence of this, which we have not really done that yet. But I expect them also to be similar. So the only way, as we proposed, the only way we can look at separate these two is to look away from the jet, where the medium response is more significant, while the jet contribution is smaller. In fact, there is a recent article, very nice article by Wang and his collaborators. They use the similar idea. They look at, for example, the baryon to meson ratio away in this region away from the jet, and they find that because there it is indeed dominated by the medium response, and medium response coming from most of that is like hydro, and that kind of baryon to meson ratio is very much enhanced, just like the thermal hydro enhancement.
Okay, it's my turn. Xin-Nian, hello.
Yes.
Usually, if you form a jet, this pattern is highly virtual, and then it goes whatever through matter. Now, most of the formula which you applied are basically for massless quarks. Now, how you do it that you get this highly virtual particle down in a way that you can apply cross sections or you can apply radiation?
Well, yes, it's a very good question, and I think there are already models existing there. For example, the model by JetScape, essentially they are taking the approach of LBT, and then instead of just consider like a massless unsure particle propagation, they really consider the 4-jet shell development within the medium. And this we have also been doing right now within the framework of what we call the generalized high twist approach. That can be done, and so far I think the result is sort of similar. It just it could also affect the final at very high PD part I'm talking about. Okay, it could affect the value of the jet transport coefficient extracting, but it will not affect the general phenomenon of the, for example, jet suppression and the modification of the jet structure itself. So that has been done so far, and we have actually done. We are developing a software package, what we call e-hygiene. So it's extension of hygiene, but focused on the electron-ion collision. And this is so LBT is completely redone, but we start from scratch, and you can just look at the medium modification to the jet shell development. Okay, so this can be done.
Okay, thank you. We have a question now from the Zoom from Yanji.
Yes, Yan.
A very nice talk. Thank you. So I just wonder, in your evolution of the median and the hard probes, I understand the median and hard probe actually feedback toward each other, but I wonder whether the median properties are also coupled together. For example, the eta over S and the Q hat, are they somehow independent things still in the calculation, or they are actually coupled within some, assumption, underlying assumption? Are they coupled together or not?
Well, very, very interesting question. So far, I think that will be the ideal case. Okay.
Exactly.
So far, well, I think we are moving in that direction. There is a new LBT model called the QLBT, is the quasi-particle. There, we're trying to introduce the picture like what what other group have done, like Catania and Frankfurt group, that we consider like the medium consider of quasi-particles. So in this case, the jet interaction with the medium is also modified by quasi-particle. So in that case, the transport coefficient is related to the jet transport coefficients within the same framework. But so far, at least for the calculation I presented here, they are sort of independent, because we on one side we just have normal hydro, and that bulk transport coefficient is essentially an input to the hydro. And on the other side, the jet medium interaction is based on potential QCD, and that is not related at all to the soft part.
Yeah, I think that would be the next level of.
I agree. So we are moving in that direction.
Thanks.
Okay, Paul Bernard has a question here from the room.
Hi, Xin-Nian. Very nice talk indeed.
Oh, hi. Yeah.
I have a question regarding one of your last comments. You said so there is no need for this crazy temperature-dependent diffusion coefficient. But correct me if I'm wrong. I thought that in the model that you developed with Xin-Nian for heavy quarks, you had this extra Gaussian kind of extra diffusion coefficient around TC. Am I right, or is it been evolved in meanwhile?
Yeah, that's what we used to do. Yes, I hope that we can probably don't have to really do that by considering what I listed here. We have not really applied this kind of framework to heavy quark yet.
Okay, thank you. To see that elder physicists like us still have a part of craziness in us. So basically, then the last question is, how do you regulate this soft gluon radiation? Because usually you have some kind of divergence there. And how technically, how do you regulate this?
We in our approach, we regulated this by the the perturbative of the bi-screen mass.
Okay, thank you.
Yeah.
Okay, other comments or questions? Not. Yes, Vincenzo.
Just a comment on the question of Paul, because I think he refers to the work on the monopole.
Yes. Yeah.
The work of Giulassi, that at type PT you have a strong increase of the Q hat. You were referring more to the drag dependence at low PT. So I think he's not against the DT dependence of the drug, but more the crazy T dependence of the Q hat at IPT or intermediate PT.
Yeah, what I most, as you said, I'm most referring to the work by Miklos and Jing Fen. So there, they said in order to describe RAA and V2 simultaneously, so at least in their model, they have to have this this very dramatic temperature dependence of Q hat, and there with I think at around the phase transition temperature, their Q hat is factor of 10 larger than than the normal extraction case. If you don't have to consider the V2 and RA problem. And I just want to say that in this case, we did not really rule out such a scenario, but at least we say that at least right now, when we take into account all the different components of the medium of the process, the coalescence model, the medium response, and also I should say that the final harmonic cascade also have some effect, in particular for the baryon sector. And after that, you really don't you can describe the V2 and RA simultaneously. I'm not quite sure whether my connection is still there.
Yes, yeah, you are still.
Because I'm working from home. You never know. Sometimes the internet connection could.
We're digesting the comments, and yeah, I believe there are no others, and not even on Zoom. So yes, thank you for your talk once more.